The object has a mass m, gravitational force mg. This is the y direction. This could be the x direction. There must be a force pushing upwards from the surface to cancel out mg because there's no acceleration in the y direction. We normally call that the normal force because it's normal to this surface, and it must be the same as mg, otherwise there would be an acceleration in the y direction. Now I am going to push on this object with a force Walter Lewin. And we know that the object in the beginning will not start accelerating. Why is that? That's only possible because there is a frictional force which adjusts itself to exactly counter my force. I push harder and harder and harder, and there comes a time that I win, and the object begins to accelerate. It means that the frictional force, which is growing all the time as I push harder, reaches a maximum value which it cannot exceed. And that maximum value that the friction can achieve, this is an experimental fact, is what's called the friction coefficient mu, which has no dimension, times this normal force. We make a distinction between static friction coefficient and kinetic. This is to break it loose, to get it going. This is to keep it going when it already has a certain velocity. The static is always larger than the kinetic. It's a little harder to break it loose. Once it's going, it's easier to keep it going. It is fairly easy to measure a friction coefficient by putting an object on an incline and by changing the angle of the incline, increasing it. This is the angle alpha. You increase it to the point that the object starts to slide down. Here is the object. This is the gravitational force mg, which I will decompose in two forces. One in the y direction, which I always choose perpendicular to the surface, and another one in an x direction. You're free to choose this plus or this plus. I will now choose this, the plus direction. I'm going to decompose them. So I have one component here, and this component equals mg times the cosine of alpha. And I have a component in the x direction, which is mg sine alpha. There is no acceleration in the y direction, so I can be sure that the surface pushes back with a normal force n, and that normal force n must be exactly mg cosine alpha, because those are the only two forces in the y direction, and there's no acceleration in the y direction, so this one must be mg cosine alpha. Friction prevents it from doing so. So there's going to be a frictional force in this direction. And as I increase the tilt, this frictional force will get larger and larger and larger, and then there comes a time that the object will start to slide. Let us evaluate that very moment, that it will get larger, this component will get larger, this component is still holding its own, but then all of a sudden it can't grow any further and it starts to accelerate. So Newton's second law tells me that mg sine alpha minus ff maximum at this point is 0. And this one is mu static times n, which is mg cosine alpha. This one is mg sine alpha. This equals 0. I lose my mg, and you see that mu of s equals the tangent of alpha. It's that easy to measure. So you increase the tilt, and then at that critical angle that it starts to slip, you have a value for mu of s, for the static friction coefficient. It is very non-intuitive that this friction coefficient is completely independent of the mass. If you double the mass, friction is often a pain in the neck, as we all know. Friction causes wear, it causes tear, and it costs fuel. It's a car, there's a lot of friction with the road. You pay for that, and people try to reduce friction with bearings and with lubrication. Oil. Water is an amazing lubricant that you begin to hydroplane, and that you literally, that your friction coefficient goes almost to zero. It happened to me once, and it's no fun. It can happen instantaneously, particularly when the rain begins, in the very early part of the rain, when the road is dusty. So you get the water with a little bit of dust mixed. It's a very dangerous situation. At home, I have a pen. This is my pen at home. Actually, I have more than one pen at home, believe me. But this is a very special pen. And what is special about it is something that I discovered purely by accident. And I want to share with you this remarkable pen. You see, when I rotate this cover, there's a lot of friction. You can hear it. And it stops. You can hear it, right? And so one evening I was boiling potatoes, and I was looking at this pen, and I walked up to it because I wanted to check the potatoes, and I touched this thing, and there was no friction. It just went spinning and spinning and spinning. I couldn't believe my eyes until I realized what is happening. Water had accumulated in the rim of this pen, and the cover was beginning to hydroplane. I'm putting water in it now. You almost don't hear it anymore. Isn't that amazing? Almost frictionless.